Again, as Hernan said, my name is Ron Lowry. I'm the Eastern Area Manager for Hazard Control. Been with the company for about 5 years now. In addition, I've got 37 years in the fire service, and I am a fire chief with a volunteer department in the state of Pennsylvania. So the webinar today is going to be on some three-dimensional fire applications and some of the difficulties we have in those types of fires and how encapsulator technology can help resolve some of those issues that we typically run into. So a little bit about the company first. Again, with Hazard Control, it's our mission to encapsulate the world. We want to make it a safer place through leadership in fire prevention and protection, utilizing those eco-friendly, innovative technologies. The eco-friendly portion of the presentation, F500 is an environmentally friendly, fluorine-free encapsulating agent, and I think the innovative technology portion will speak to itself as we go through the webinar. The company is Hazard Controls, located just outside of Atlanta, Georgia. All of the agent is manufactured at our facility right there in Atlanta. But as you can tell from the webinar today, we do have a global presence. So we have either a subsidiary company or distributorships on every continent with the exception of Antarctica. So it definitely is a global product, US made with global reach. Same way we understand the importance of being out there in the industry. We're members of the NFPA. There are several employees that sit on various NFPA technical committees. We do help with some information in the IFSTA for the various firefighting manuals. We are members of the Society of Fire Protection Engineers, and the company is an ISO 9001 registered company. So we have that very strict quality management system in place. Gives you peace of mind that the products you buy off of us today will be the same quality that you'll get a year from now, 5 years from now. So we kind of pride ourselves on that ISO registration. So we have, the new technologies today that are creating new hazards that need to be addressed. Lithium ion batteries, particularly the three-dimensional fires, what we're here to talk about today. Other things like Class D metals and solar panels. So in particular, for today, we're going to talk about three-dimensional fires, the chemistry of that fire, encapsulator technology, and the features of encapsulator agents, the applications on of encapsulator in the particular application on those three-dimensional fires. So the main objectives for today's webinar is to achieve an understanding of what that three-dimensional fire is and the differences between foam and encapsulator agents and water additives when it comes to trying to fight those three-dimensional fires. We want to explain the characteristics of an encapsulating agent and its application, and then we'll talk about some of those different particular three-dimensional fire applications in today's webinar. So what is a three-dimensional fire? For the most part, it's a burning fuel that is spilling or cascading from a higher plane to a lower altitude. So it's three-dimensional in nature. It's not a two-dimensional pull fire. We're talking about things like tank trucks, well heads, distillation columns, flange fires, compressors, those type of things. And when we talk about the specific agents that are out there that we potentially could use for those types of fires, there are mainly three. So you have your NFPA wetting agents, NFPA 11 foams, and the NFPA 18A encapsulator agents. With a wetting agent, the only real purpose of a wetting agent is to make that water wetter. So reduce that surface tension and allow it to flow easier. Really gives you no solution for that three-dimensional Class B fire because just like using plain water, the fuel's just going to float on the surface of that. Really isn't going to be a good solution, just like water is not a really good solution for the Class B three-dimensional fires. Your NFPA 11 foams, again, are surface tension reducers that helps spread that blanket on the fire. That blanket is meant to separate the fuel from the oxygen, but as we'll see as we go through the presentation, with a three-dimensional or a flowing fuel fire, you really can't form that blanket. So you can't maintain that blanket over a three-dimensional object. Makes it extremely difficult. Up till the invention of encapsulator agents and the acceptance of the encapsulator agents, we tried to use, we still try and use a lot of foams for those three-dimensional applications, but they really aren't particularly well suited for that type of fire suppression. And lastly, we have the NFPA 18A encapsulator agents, again, who's, you know, they're a surface tension reducer just like the other two agents. But in addition, the encapsulator agents can actually encapsulate the fuels molecularly, rendering those fuels non-flammable. They change that heat reduction mechanism of water to make the water absorb more heat, thereby removing the heat in that three-dimensional fire application. And some testing that shows we can interrupt that free radical chain reaction as well. So on that three-dimensional application, the agents are actually pretty effective because, again, they're not relying on that bubble, that blanket structure. So when we look at basic fire chemistry, we know from the fire tetrahedron, we need to remove one leg to suppress the fire. And if we're trying to do that with a foam, we're trying to lay that blanket down here to separate the fuel from the oxygen. But just if, you know, we would have a fire on this triangle when it's floating, flowing down the side, again, it's impossible to form a fire or form a blanket over this three-dimensional object. So again, one of the reasons that foams, unless you're trying to do a dual agent suppression, are really ineffective. So let's look at those potential fire protection considerations for a three-dimensional fire. So as we said, water or wetting agents, they're really inefficient at reducing the heat. They're only using that outside surface of the water to turn to steam. Don't really work well on Class B fuels. That fuel can actually float burning on the water and spread the fire. Your foams, both Class A and Class B, great on a two-dimensional fire application. You know, they can spread out across the surface of a two-dimensional fire contained within a, you know, an above ground, a storage tank in some type of retained area. Really, a really great suppression capability there for those two-dimensional fires. But again, doesn't really work in that three-dimensional plane. Encapsulator agents, we can rapidly reduce the heat. To remove the heat, we can encapsulate the fuels, rendering those fuels non-flammable so we can remove the fuel. We can also interrupt that free radical chain reaction. And it's very effective in not only the 2D plane like a foam, but also in the three-dimensional Class B plane. In fact, if we look at the NFPA 11 Annex A11, it actually states right in the foam standard that foam is not suitable for a three-dimensional flowing liquid fuel fire or a gas fire. So while right within the standard, it states that those agents aren't really affected for those types of fires, again, up until encapsulator technology, that's what the fire service and the fire protection industry tended to go towards, even for that type of fire, sometimes with pretty damaging results and dangerous results, as we'll see as we go through this. So if we look at encapsulator agents, what is an encapsulator agent? Again, it's covered under NFPA 18A. F5 or Hazard Control Technologies kind of invented the technology back in 1996. The agent provides, as I said, the superior cooling properties. It's effective on Class A, B, D, and lithium-ion battery fires, as well as both pressurized fuel fires and those three-dimensional hydrocarbon-based fires. We feel this is the technology for the next millennium. Again, this UL class, the agent has the UL classification for both A and B. And again, we're waiting for that classification to catch up for the lithium ion battery application. Within 18A in particular, the agent falls under this section 7.7 encapsulating agents. It's the spherical micelle stability test. This is right from the NFPA 18A manual, that this particular section covers the test procedure to evaluate the ability of a water additive solution to form and maintain stable spherical micelles that are capable of encapsulating combustible liquids, both polar and non-polar, rendering those flammable liquids non-flammable, non-ignitable, and non-explosive, and then maintaining that encapsulation in the presence of high heat over an extended period of time. So again, kind of based off of that definition, what is an encapsulating agent? And it's a water additive whose basic building block is that spherical micelle. Again, they're capable of encapsulating both hydrocarbon, polar and non-polar liquids, and more importantly, vapors. So we can do vapor state encapsulation as well, separating that fuel from the oxygen on a chemical molecular level. Real quick animation here that's kind of going to go through the encapsulating agent and what happens when it mixes with water, and what that spherical micelle is and how it comes to be.
Encapsulator technology, the next generation of fire and hazard mitigation. First, we start with a simplified version of a single encapsulator agent molecule consisting of a hydrophilic polar head which loves water, dissolves in water, and a hydrophobic non-polar tail which fears water and will do anything to get away from water. Once the EA molecules enter the water, they instantaneously and automatically orient with the non-polar tails inward and the polar heads outward, forming millions of spherical micelles. Micelles travel towards and exit the nozzles, forming EA droplets. Micelles nearest to the surface of each droplet automatically break apart. The nonpolar tails orient outside the droplet with polar heads on the surface, forming an EA skin on the surface of every droplet. In addition to the EA skin, there are millions of molecular spherical micelles within each droplet.
So this orientation of the agent both on and within the water droplet is what makes it do what it does. And we'll actually get into this in a little more in-depth as
encapsulator technology
here. So when we talk about those spherical micelles, it's kind of hard to tell from that animation, but again, we're talking about molecular structures and how many of the micelles were actually there. Again, you would need an electron microscope to actually see those micelles within the water droplet. And that's one of the difficult things when we talk about encapsulator technology, because when you're comparing it to a foam, you know, we can easily see the bubbles, but you really can't see the micelles aside from, you know, the water actually going from a clear liquid to more of a white milky liquid that you know that you have agent in the water stream. But as a comparison to how tiny those micelles actually are, if the Earth was a water droplet, those micelles would be the size of a pea in comparison. So just to give you some idea of the amount of micelles that are contained in every water droplet. So again, we have those unique features of an encapsulating agent, rapid cooling encapsulation, the toxin reductions, and then also all of that with also the ability of being fluorine free. So that first unique feature, that rapid heat reduction, where the heat is drawn rapidly into the internal portion of the water droplet, particularly important in some of those three-dimensional applications where, you know, it is as important as encapsulating the fuel is removing that heat and remove.
Hazard Control Technologies presents F500 encapsulator technology.
So we have a piece of sheet steel here. It's that they're actually going to use a torch to heat that steel up, and they'll actually be monitoring that temperature with the thermal imaging camera. So you can see the paint surface ignites even though it's not being come in contact with the actual flame of the torch, because that material's been heated up enough that it's reached the auto ignition temperature. Now you'll see the agent will be applied to the back half. Notice that surface fire was just extinguished. Again, the agent cooled that steel below the auto ignition temperature of the fuel, extinguished the fire without ever really touching the fire. As you can see here, rapidly dropped the temperature down to about 81 degrees Fahrenheit. The demonstration here, the guys at the scrapyard to go up and put their hand on that steel that was in excess of 1,000 degrees. So again, that rapid cooling, removing the heat, removing that ignition temperature on those fuels. The next unique feature, again, is that encapsulation. As I said, we test that under the NFPA 18A Section 7.7 spherical micelle stability test. That test protocol is actually part of our ISO 9001 quality management system. This test is run, excuse me, on every batch of agent, every lot of agent that's manufactured. That formulation for us for F500 is a 1 to 8 to 40 ratio. 1 part F500 to 8 parts fuel to 40 parts water minimum, plus the kinetic energy of that water leaving the hose stream. So again, video here actually showing this spherical micelle stability. What we're going to do here is we have a gallon of gasoline to 16 ounces of F500. So that's our 1 to 8. And then we're going to go ahead over the course of a minute and add in 5 gallons of water from that hose. So what we have here, again, is we're going to add the gallon of gasoline to the pan. We're going to mix in the 16 ounces of the encapsulating agent, in this case, F500. And then we're going to go ahead over the course of a minute and agitate that water into that mixture of both the fuel and the encapsulating agent. So the next part of that standard is that the solution needs to sit for a minute. So at the end of that minute, you need to take a torch, and you have to be able to pass a torch across the entire surface of the fuel without having ignition. So as you see here, we are adding heat to that fuel mixture, that gallon of gasoline, 5 gallons of water, and 16 ounces of F500. What we're showing here is we have a stable spherical micelle that is holding on to that hydrocarbon molecule and not allowing it to get to the oxygen so that it becomes ignitable. Now, if you had a good foam blanket down there, you may get a little candling, but you wouldn't get a full flamed ignition because the foam would be doing its job. It would be suppressing those vapors. So the second part of the test is that we need to come back 2 hours later and perform the same test. So I know it's kind of time lapse, but as you can see, the ground's dry. All that water that was squirted on the ground is now evaporated. And again, we're passing a torch across the surface of that solution without having any ignition. So here at Hazard Control, we've run that 1 minute test we've run that 2-hour test. We've also done a 2-day and a 2-week test to show that those micelles stay stable over a very extended period of time, holding on to those hydrocarbons and not allowing them to ignite. Again, one of the reasons we can work in that 3-dimensional application is because we're not relying on a bubble. We're relying on the micelles to remove the flammability of that fuel. Lastly, is this the reduction of the carbon, the smoke, the toxins within the smoke due to the ability of the agent to interrupt that free radical chain reaction. So the testing that was done to show this was done at Clemson University, where they were burning toluene. They did multiple burns where they injected a plain water mist just into the smoke column. So they were looking to just treat the smoke, not extinguish the fire. Then they matched those burns where they injected, but the difference is they injected a 3% solution of F500 into those smoke column, again, to compare the results. They were looking for like light transmittance through the smoke. So what was the opacity or the density of the smoke? How much of the byproducts of combustion actually were generated inside that inverted funnel? So the soot that was generated, and then the toxicity of both that soot and smoke. The comparison results they came up with when the F500 was used is there was a 68% increase in visibility, a 97% reduction in soot, and a 98.6% reduction in soot toxicity. So the ability to actually remove a lot of these very cancerous, very dangerous toxins out of the smoke, and improving safety and improving visibility and overall environmental concerns when the agent is used, particularly on those highly toxic Class B type fires. Animation to drive home that point of that toxin and smoke removal. So we have 5 burning tires here generating that heavy black toxic smoke. We're going to be using a 1% solution here where the testing was a 3, but this is only a 1% solution. Watch the smoke. So we still have burning tires, but we're no longer generating that heavy black toxic smoke. That's the interruption of the vapor phase combustion, inhibiting the creation of that heavy black toxic laden smoke. So the ability to actually reduce the smoke drastically from those very smoky, very toxic fires. Again, as we said, the agent is free with everything that comes with that. Some of the advantages, it's non-corrosive, non-hazardous, fluorine-free as tested through the EPA's 537 modified test. And the agent is also 100% biodegradable, listed on the EPA's National Contingency Plan as a surface washing agent. So now that we know what the agent's capabilities are, let's look at these particular applications around the Class B polar, non-polar, 3-dimensional type fires. Just a real quick introductory video here. We'll work over the various classes of fires that the agent is capable of suppressing, in addition to those 3-dimensional Class B fires. So everything from your prototypical Class A, woods papers, again, rapid knockdown, burning tires. We'll see the same thing here. That heavy black smoke disappears even though the tires are still burning. Vehicle fire, you'll notice the same thing, how rapidly that heavy dark smoke disappears. Again, rapid knockdown. the two-dimensional Class B fire application. So this is diesel fuel. So again, as you can see, no special application technique. Ethanol, E85 gasoline, so both polar and non-polar. And now here's the first look at that three-dimensional application. So this is jet fuel through a simulated jet engine cowling. So we have a three-dimensional running fuel fire. Impossible to form a foam blanket over. Again, vapor encapsulation, propane, not just liquids, but vapors. Lithium-ion batteries. Class D metals, it's magnesium. And another one of those three-dimensional Class B applications. So this is a substation-based transformer in Westchester County, New York. So again, three-dimensional Class B fire. That one not running, but still a three-dimensional Class B fire. So some of those three-dimensional fire applications, things like under turbine lube oil, transformers, the pipes and the manifolds, the distillation columns that you may find in tank farms or refineries. So let's look first at what happens when we try and use foam on some of these three-dimensional fires. So here you'll see it's a tank truck that had caught fire and is burning. And unfortunately, the tank got so hot that it ruptured. Again, we now have not only a three-dimensional, but a running fire. People don't think about the three-dimensional fire applications of a vehicle fire, but that's exactly what it is. We have both fuel on the ground and burning inside that three-dimensional vehicle. Again, as we can see here, you know, even with the foam blanket being down now after the explosion, again, you still can't maintain that three-dimensional blanket. You know, larger fire scenario here where you're going to have a running fire, not just, you know, that three-dimensional, but as you have here, they're using water. The fuel's actually burning on top of the water that they were using, now running out of the building, that burning fuel engulfing $1 million fire truck. Some of the other methods that we currently use, we talk about those dual agent applications. So we're going to be using foam here to start a blanket within the two-dimensional aspect of this fire, while they're using Purple K, so that dual agent application to try and extinguish the entire fire.
You're welcome.
So again, when you have that superheated steel with the foam, it's really difficult for that foam to seal that fuel off. So that's why you need the dual agent approach. Try and suppress the fire actually with that chemical agent while the foam's coating the fuel over, trying to separate that fuel from the oxygen. But again, it needs to form that blanket up to and including that superheated steel from the fire being around it, which makes it extremely difficult to do because, again, that that steel is superheated, and putting a blanket on it really doesn't reduce the temperatures. Again, dual agent application here, we can see the purple K going on while they're applying both water and foam to try and cool the steel, put a foam blanket down, and use the purple K on those three-dimensional type fires. That flowing three-dimensional that you can't form a blanket over. But as you see, you still need the dual agent approach. You need the water to try and cool the steel while you need the purple K to put the fuel fire out, because neither agent can do it by itself. If you put the fire out with the purple K, as soon as you run out of purple K, the steel is still superheated. The fire is going to reignite. You can cool the steel, but if you can't extinguish the flowing fire, you're never going to put the fire out. Let's look at some applications of F500 on these particular same type of scenarios with an encapsulating agent. So three-dimensional flowing fire, a distillation column, a well valve fire, so a broken valve. Again, three-dimensional flowing fuel. You have that jet of fuel coming out, plus that two-dimensional pool fire like we just had previously. Again, that jet engine cowling, flowing jet fuel, so a turbine, flowing fuel fire. Notice the fuel's still running. Here we have a flange fire. So the same thing, flange let go, compressor station, those types of fires where you have that running three-dimensional fuel fire. We're cooling the surrounding steel structure while we're encapsulating the vapors. Same way here, just breaking that vapor column, encapsulating the fuels. Another flange fire here. So again, all those various fires we see agent applications, again, handled with a single agent.
Hazard control.
A good example of that three-dimensional flowing fuel fire. So this was actually from a refinery over in Italy with some testing they were doing on F500. So we're going to have here is diesel fuel being pumped down that steel inclined plane. So we have a three-dimensional, again, it'll be a three-dimensional running fuel fire with that two-dimensional pool fire at the bottom of it.
Flowing diesel fuel fire. The fuel was ignited in the 7 by 10 foot pan. The inclined metal plane was allowed to build up heat. Notice the flowing diesel fuel continues to flow through the exercise. NFPA 11 Annex A 11 states foam is not suitable for three-dimensional.
As you see here, the agents, the firefighter, the first thing he's doing is attacking that steel plane, trying to encapsulate the fuel, starting to cool that steel off, remove that ignition temperature, remove the heat from that steel to try and prevent it from reigniting the fuel as it's running down it. Now he's going to go after that, the fire at the base. Again, continuing to cool the steel while he hits those corner pockets of fire. As you see, the fuel's still running down the plane. Again, rapidly suppresses that fire with one agent. A great video here for actually fixed fire applications. So
Hazard control technology guns F500 encapsulated.
What we have here is F500 being teamed up with a rotating fog nozzle. So a fixed system type application that not only can extinguish the fire, but can prevent the fire by encapsulating potential flammable vapor leaks before they ignite. So the ability to prevent an explosion as well as extinguish the fire. So again, three-dimensional flowing fires. The F500 partnered with that rotating fog nozzle actually gives you a superior three-dimensional extinguishing capabilities from a fixed system type application. Sets out a wide spray of an encapsulating agent fog. Again, even if you had a vapor release, encapsulate those vapors or extinguish the fire. You see here a fuel fire. So this is gas. So that's a three-dimensional gas fire. Again, both the liquid and the vapor state encapsulation, fire and explosion prevention. So here's a good side-by-side comparison. This is thanks to our distributor over here are side-by-side with the same tank truck simulator. One fire, that three-dimensional fire that's going to be attempted to be extinguished with AFFF foam. And then on the right side, we have the F500 encapsulating agent on that same type of fire. So on the right, they're just using two hand lines to attack the fire with a 3% solution. On the video on the left, they haven't started a foam application yet. They're just trying to cool down some of that steel so that the foam is actually effective when they go to apply it. So they're trying to cool the metal, cool the steel to make the foam more effective. So we can see the video on the right. The F500 has actually suppressed the fire already. We're just now continuing to cool the tank, remove the heat from the tank, prevent any reignition by cooling the tank below its auto ignition temperature. Starting to see the foam application. They're now starting to apply the foam onto the tank fire. Again, trying to cool the fire, control the fire below the tank. So they've now shut down the water lines so that they aren't affecting the actual foam blanket. But again, as you see, we continue to have that running fire that the foam can't form a blanket over, can't really extinguish the fire. So as we're looking at this, just think as a comparison, the amount of product that's been used with the F500 to suppress the fire compared to the ongoing effort with the foam, the quantity of product that's needed to try and put these fires out, and the environmental impact of all that product. You know, it's not only the fuel that continues to burn and continues to flow, but also if you're not using a fluorine-free foam, the environmental impact of the amount of foam that's being used to try and suppress that fire. So as you see, we now have a small fire at the front of the tank again. Again, not only trying to cover the fuel, but remove that heat. They need to remove the heat from that fire. So again, drastic difference comparing the two products there side by side. So again, various equipment and systems that are available for both manual and automatic fire suppression. So CCS systems to help cover pipelines, manifold valves, three-dimensional either loading racks or rack storage systems, portable delivery equipment, the turbo cannon, the trailers, compressed air systems, gives you the ability to provide direct application on three-dimensional fires with really no specialized equipment like foam nozzles, those type of things that are required for foam applications. Again, just another quick video here of that Veep system that we saw, those rotating nozzles. The agents available in either bladder tank configurations for fixed systems or the water-driven proportioners. Again, the mobile equipment, be it F500 trailers, our quick attack mobile units, F500 carts, extinguishers. We also offer consulting and training on various types of fire hazards, emergency response, the concentrate testing for the fixed system type applications. In some of the industries that are dealing with combustible dust, we offer a dust hazards analysis. Again, also training in emergency response, lithium-ion battery hazards, solar panels, energy storage systems, and the modern car fire training. So in summary, you know, the encapsulating agent is a unique agent, particularly for the various categories of fires. It fights fires in unsurpassed ways, encapsulating the hydrocarbons, reducing the heat, rapidly reducing the heat, and inhibiting the creation of smoke and cancer-causing toxins. It's really unsurpassed for both two-dimensional and three-dimensional Class B fire applications. It can be used in fixed suppression systems, direct applications in energized environments like we saw in the beginning, that transformer fire up there in New York. And it gives you the ability to inert those flammable gases, like with the Veep system, to actually eliminate the fire as opposed to respond to it, eliminate that combustible atmosphere, that flammable atmosphere before the explosion or the fire actually happens. Just thank everybody for your time. I hope you found it informative. Again, if you have questions, please don't hesitate to reach out to any of us. You know, we're here to support our customers. Stated at the beginning of the webinar, you know, it's our goal to make it a safer world out there using this technology. And I think we all honestly believe we can do that. Future questions, don't hesitate to reach out. If you don't have specific emails for folks, you can always do the info@hct-world.com, and Esther will get it routed to the correct person to get you an answer. But thank you for your time, and I hope everybody has a great evening, day, morning, depending on what part of the world you're joining us from. Thank you.